And so now that we're using our rose graph exploration that we did, we kind of took a look at some of this stuff self-guided to kind of see what you came up with. First couple of pages are explanation, but they do remind us what we see here at the beginning of our 8-5 notes. We need to make sure that our format is still in our polar GC. So I'll do this here on my calculator to make sure I'm in the same place. So I'm checking that my format here is still in polar. When I go to mode, then I'm in degree mode and polar form. Our rose graph exploration was all done in radian mode, so remember that we can use radians as well, but we are much more familiar with degrees. And that when we go to graph, most of the time we're going to do a zoom 6 or a zoom 0. And some of us saw that this zoom 1 may also be helpful. All right. Now, last time in our section 8.4, we were looking at things that looked like this, where we had a coefficient in front of our sines and cosines, and that we were calling that b before. And then we had other things that we were adding to it, and we were calling that a before. So we're going to continue to use those same letters. And as we were looking at these things, we call them rose curves. They look like flowers. And we started seeing that they're in this form, like this one that we have here. So our form that we're seeing is an r equals b cosine n theta, or r equals b sine n theta. And the big thing that's new that we've added in with these rose curves is this coefficient in front of our angle measure. It's that coefficient that changes these graphs into the way that we're seeing during our exploration. So we start seeing exactly what this thing is telling us. We start looking at these neat looking graphs, and you're starting to see some different new pictures that we can see. And as we went through this exploration, it asked us to graph certain things. Jenna, would you mind explaining to me what you saw in these two graphs here that made them different from each other? Here, I think we were seeing just the same graph up here kind of thing. But what made this graph different from the second graph that you had? It was smaller. Awesome. So this one was a nice small little rose graph. This one that we had over here was certainly much larger petals. So it should have been a very distinct difference between these two. When you looked at these differences, Devin, did you get an idea about our petal length between these two graphs? What did you find for our first graph, petal length of?
1 unit, and the other one was 3 units.
Awesome. So our first one was 1 unit, our second one was 3 units, and judging by my picture, if this is matching yours, they each had 3 petals. So what this tells us is, since the only thing that changed from this equation to this one was our coefficient out in front of the trig function, that value is b, and that is what controls our petal length. So as b directly is related to the length of a petal. This means if our b value goes up, our petals get longer. B value goes down, our petals are shorter. Let's transfer that also to our note pack that we have here. What we're seeing is the length of each rose or each petal is directly related to B. So in this example, I don't have a coefficient out in front. That means if I don't have one there, is it 1 or 0? 1. Awesome. If it doesn't have a coefficient, we don't want it to end up being 0. It's going to be a coefficient of 1. So these petals that we see here are going to have a petal length of 1. All right. I don't know what else we're going to see there, but let's keep on thinking about what we saw farther in our exploration. We started seeing this, we started changing the values of a different coefficient. Here we only changed the coefficient in front of the angle. Shay, can you explain to me a little bit about what your two angles looked like, or what your two graphs looked like here, please?
The amount of petals increased.
Awesome. Our number of petals increased. So in this first one, how many petals did you have over here?
5.
5 petals over here. So we saw 1 and a 2 and a 3 and a 4. Kind of looked like that. Now mine, they look pretty sad. My flowers are always kind of wilty. And then how many did you see over here in our second one?
7.
7. Awesome. So it matched that number exactly that we had, that coefficient. Over here we had 7 petals, and 1, 2, 3, 4, 5, 6, 7. Again, a really bad lopsided looking flower. So it was very easy to think that whatever that number was out in front is exactly how many petals we came across. But then perhaps you saw this angle here. Mitchell, would you tell me what these graphs looked like down here? Because I'm expecting 2 petals and 4 petals. What did you find?
I have, for the first one, I have a plus sign.
Okay. Awesome. So it kind of looked like a plus sign, something kind of like this.
And the other one had 8 petals.
And our other one had 8 petals. All right, so it had like the 4 here. And then kind of another set in between, right? Yeah, another fun lopsided flower. So all of a sudden something changed when we had this value for n. It looked like at first it was just every single, whatever that value was how many petals we had, but then it changed when we saw this. What we're going to see is that the number of leaves is determined by the n value, but it makes a difference whether it's even or odd. If n is even, the number of leaves that we're seeing, or the number of petals, is twice n. If the number is odd, we're going to just take n by itself. Now what we're actually seeing is that they are the same numbers. It's just when they're odd, they're drawn on top of each other. So there are actually 6 petals there. It's just that it's 3 and 3. They're just on top of each other. So we aren't seeing all of these petals here. All right. So here we're seeing 2. If we had 3 petals, there are actually 6 petals, but they're right on top of each other. So we only show up as 3. Now we call this graph a rose petal curve. Or just a rose graph is another way we could call this. And in this case, I see that we have an n value is 2. 2 is an even number. So how many petals would I be seeing? 4. Awesome. So when I graph this, if I were to go ahead and graph this new one here on our grid, sine of 2 theta, I'm actually seeing 4 petals like this. All right. And we can look at our table of values. It'll show us over here where those petals would be. I know they have a length of 1, so I'm going to go ahead and put them out to this radius of 1. And with my knowledge, I know that they're going out to 45 degrees. So I'm going to go ahead and draw our 4 petal graph. What we're seeing is essentially something that looks kind of like a 4-leaf clover. But we call this a 4 petal or a 4 leaf. It can be called either way, 4 petal or a 4 leaf. Now this is an important one. Right here, cross off that A and make that a B. Sorry about that little typo. That could cause some serious problems. The easy way to graph these is to use our values of B and N to tell us what its longest length is. So B is here, B is 1. So our length of our longest petals are 1. N equals 2, which is even. So we're going to have 2 times 2, which is 4. That tells us we have 4 petals. Now, since these are going to continue to get more and more complex, we have this way about how we can find rose petals and how we can graft them really nicely. We start, first of all, by finding out where our first petal occurs. If I go to my table setup now, if we have it the way that we had it set before, where we were graphing from 0 to 30 degrees, our table before is how we would have had it set like this. Oops, my goodness. 0 and 30. There we go. And so I'm seeing values at 30 degrees. I can use this to graph, but I don't ever see a radius of 1, the longest length that we should be looking for. So what we'll get in the habit of doing is going to our table setup, starting at 0 and changing by every 1 degree. This is going to seem a little tedious at first. But what it does is it allows me to see every single angle in my table now. And I'm looking to find where the length is 1. I'm expecting to see a length of 1. It told me right here, my B equals 1, so I need to find where this first longest petal occurs. So I'm scanning my radius for a length of 1. I can use these values along the way to graph my first petal, because I'm also going to want to know if I have a really narrow petal or if I have a really wide petal. So I can use these values along the way to do that. And I'm getting closer and closer until right here at 45 degrees, I see I find my first length of 1 appears at 45 degrees. This gives me this first petal right here, a length of 1. My first petal is drawn. I need to find 3 more petals. So I can now change my table set to go from 0 to 45 degrees. I can do that now if I know that that's where my first one is. So from 0 to 45, I'll now see where all of my other petals are showing up at. But there's also another way to go about this, and this way I actually think is easier. If I know that there are 360 degrees in a circle, and they're evenly divided among 4 petals, I can take 360 and divide it by 4. What this tells me is that a petal will occur every 90 degrees. I still am using this method to find where my first petal is, but once I know where that first petal is, I can add 90 degrees to it to find all the rest of my petals. Once I know that, I can also use my table to find other values along the way to figure out how wide or how skinny my petals are.